The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.eu and I'll respond as soon as I can. All right, so now we're going to look at section 11.4. So we've been looking at exponential functions or exponential equations, and let's see, we had something like this. Well, how about 2 cubed equals 8, all right? And 2 to the 4th power equals 16. But what if I had 2 to the x power equals, let's say, 11, okay? Can you see that x has to be bigger than 3 and smaller than 4? Is that obvious? No one's going to answer. Okay, fine. Yes, x has to be between 3 and 4. But what is it? Well, I suppose we could trial and error, go 2 to the 3.1 power, 2 to the 3.2 power, 2 to the, etc. And over time and trial and error, we could get as accurate as we needed to. But there's a better way to do that, where we have a situation where the unknown is the exponent. And that is something called logarithms. We can rewrite 2 to the x power equals 11 as log base 2 of 11 equals x. Now, that still may seem strange if you've never dealt with the idea of logarithms before, but at least can you see that I've now isolated x? So if I knew how to figure out what that was, I could figure out what x is. And that's what we're going to be doing here in the next few days, is figuring out what that is. We're going to come back to that eventually. But what I want to look at now is how I got from here to there, okay? And then also how we get back again. And that is the idea of changing an exponential equation into a logarithmic equation, okay? So let's say I've got y equals 2 to the x power, okay? That would be the same as log base 2 of y equals x. Now, this is a two-way street, and let's look at how we get there, okay? In this exponential equation, 2 is called the base, all right? And then this is the exponent, and this is, I guess, the result or whatever. But over here, we say log base 2 of y equals x. So here, 2 is the base also. What I want to do is I want to talk about an inning of baseball for just a minute, okay? In an inning of baseball, you have two teams. You have one team that's up to bat and the other team that's out in the field, okay? After the team up to bat gets 3 outs, the players change places. The team that's up to bat goes out in the field. The team that's out in the field goes up to bat, right? Well, now out in the field, there's this baseball diamond that has bases on it. When the teams trade places, does the team out in the field pick up the bases and take them into the dugout? There's an expression, he stole a base. Is that what they mean? No. The bases stay in the same place, right? The bases stay the same, but the players change places. And that's how I like to describe this. Going from exponential form to logarithmic form, the base stays the same, but the players change. So for instance, if I have 2 cubed equals 8, this would be log base 2 of 8 equals 3. The base is the same, but the players change places. Now, careful though, this is 2 to the 3rd power. This is not 2 to the 8th power. This is log base 2 of 8. So it's not a power situation like it is over here. But the base is the same, the players change places. Let's apply that to the following examples. Here we have, let's see here, we have log base 3 of 81 equals 4. And it says, write each logarithmic equation as an exponential exponential equation. So the base is 3, so this would be 3 to the 4th power equals 81. So logarithmic equation, exponential equation. Base is the same, players change places. Okay, let's take a look at another example. Log base 7 of 7 equals 1. So 7 to the 1 power equals 7. Base is the same, players change places. And this one, log base 10 of 100 equals 2. This would be 10 squared equals 100. Base is the same, players change places. How about this one? Log base 6 of 1/36 equals -2. 6 to the -2 power equals 1/36. Everybody getting this okay? Any questions? Anybody confused? All right, we'll keep going. Log base 8 of the cube root of 8 equals 1/3. That would become 8 to the 1/3 power equals the cube root of 8. Aren't those equivalent? Exponential radical form. Okay. How about this one? Log 0.01 equals -2. What's missing? There's no base written. Okay, now as you probably know, math people try to be efficient. If there's something that's used over and over and over a lot, they have a shortcut notation. For instance, if you're taking the cube root of 8, you put a 3 in the index. But if you're taking the square root of 8 or the square root of something, they don't bother to put a 2 in the index. It's understood that if there's no index, it's an implied 2. Okay, now, log base 10, which is also known as common log, is used so frequently that math people decided we're just going to write log with no base, and everybody has to know and understand that that means log base 10. Okay, so log is the same as log base 10. In fact, if you look on your scientific calculator, you will see that there is a button that says log. It's over on the left side up towards the top. And if you look at the second function key, it's 10 to the x. So that's a good way to remember that log is the same thing as log base 10. All right, so having said all of that, in fact, let's put that implied base in there. So this becomes 10 to the -2 power equals 0.01. All righty. Let's see here. How about this? X equals log base 9 of 81. So 9 to the x power equals 81. N equals log base b of r sub 1. B to the n equals r sub 1. All right. Now we're going to go the other direction. We're going to take exponential equations and write them as logarithmic equations. So 8 squared equals 64 becomes log base 8 of 64 equals 2. Base is the same, players change. 10 cubed equals 1,000. Log base 10 of 1,000 equals 3. 3 to the -4 power equals 1/81. Log base 3 of 1/81 equals -4. B to the r power equals 2/3. Log base b of 2/3 equals r. Okay with that? Any questions there? So you need to be fluent in going back and forth between the two forms, because just about all the time, if you're solving an exponential equation, you end up converting it to a logarithmic equation to solve it. And if you're solving a logarithmic equation, you end up converting it to an exponential equation to solve it. Not all the time, but most of the time. Okay. Let's see here. Let's take a look at this. Log base x of 9 equals 2. It says solve for x. Okay. So what do we have here? We have x squared equals 9, right? Writing it as an exponential equation. Okay. Now, let's solve this thing. Well, we could use the quadratic formula, but before we learned that, we used the square root property. I couldn't think of the name of it. So let's use that because it's already in that nice form. So x equals plus or minus 3. Okay. Now, we have a small problem though. It turns out that x can't equal -3, and let's find out why. So in fact, the only correct answer is x equals +3. Even though -3 fits in here, it won't fit over here, and let's talk about that, okay? Let's say we have y equals b to the x, all right? What do we know? We know the base is greater than 0. The base can't equal 1. The domain is what? All real numbers. And the range is greater than 0. Remember, we've got this graph that looks like this or like this. So the base has to be greater than 0. The base can't be 1. The domain's all real numbers. The range is greater than 0. Okay, that was going back to the previous section. Now, let's take this and let's change it into a logarithmic equation. Log base b of y equals x. Well, this b is the same as that b. This x is the same as that x. This y is the same as that y, because we've changed form, but it still has the same restrictions to each thing, okay? So over here, we said b has to be greater than 0. So that means over here, b has to be greater than 0. Well, if b has to be greater than 0, it can't be negative. Okay, let's go further with that. X, the exponent here, can be any real number. So the answer can be any real number. We can get an answer over here that's positive or negative or 0. But y has to be greater than 0, which means y has to be greater than 0. So what does that mean? That means that when we're taking a log of something, the base has to be greater than 0, and it can't equal 1. The answer can be any real number, but the quantity that we're taking the log of has to be greater than 0. Okay, so this has to be greater than 0 and not equal to 1. This has to be greater than 0. This can be any real number. Those restrictions carry over from its exponential form. Okay, I know that's a lot to swallow. Let's see here. How about this one? Log base 27 of x equals -1/3. So solving this logarithmic equation, we're going to change it into an exponential equation. 27 to the 1/3 power equals x. Well, 27 to the -1/3 power equals x. Well, that would be 1/27 to the positive 1/3 power, which is what? The cube root of 27. So x equals 1/3. All right. Let's see here. Log base x of 0.001 equals -3. X to the -3 power equals 0.01. Well, here's the thing. If we could take the right side of this equation and write it so that it either had the same base or the same exponent, we could solve for x. But 0.001 is 1/10, 100th, 1000th, isn't it? Okay. So wouldn't that be 1/10 cubed? You see how I'm getting there? 1000 is 10 cubed. But that could be written as 10 to the -3 power. Now, usually, in fact, back in beginning algebra, we taught you if you have a negative exponent, do the reciprocal of the base, change the exponent to a positive situation. So here I am taking a positive exponent and making it negative. Why? My motive is different. I'm trying to match this. So if x to the -3 power equals 10 to the -3 power, then x equals 10. Now, I'm using some ideas that we skipped in Math 93, so it's not like the -3's just disappeared, but we're not going to go into those details at this point. We're just going to say this. If we have the same exponent, then the base would be the same in this context. Okay? So x equals 10. In fact, let's do this. On our calculator, let's find that button that says log, okay? And we want to take log base 10 of 0.001. So I'm going to turn the calculator on. I'm going to push that button. And when I do, it looks like this. Okay. Then I'm going to put in 0.001 and close it up and push equals, and I get -3. If you have your calculator there, try that. If you don't, later on, do that, because we're going to be doing some calculator stuff here in a minute anyway. Okay. How about this one? This is going to be tricky. So here we go. Log base 4 of 8 equals x. Okay. I need to solve for x. I'm going to change this into an exponential equation. So it's going to be 4 to the x power equals 8. Now, in the previous problem, I solved for x by getting the same exponent, right? I got it so that the exponents matched, then for the bases had to be the same. Well, here I'm trying to solve for the exponent. If I could get the bases to be the same, then the exponents would be equal. I don't know how to take 8 and write it as 4 to some power, okay? At least not off the top of my head. But be careful now, watch this. Can you see that 4 is a power of 2, it's 2 squared, and 8 is a power of 2, it's 2 cubed? So what I'm going to do is this. I'm going to take the 4 and I'm going to write it as 2 squared. Okay, so 4 becomes 2 squared. So instead of 4 to the x, it's 2 squared to the x. But recall, a power raised to a power, you multiply the exponents together. Okay, so 4 to the x is 2 squared to the x is 2 raised to the 2x power. Now, 8 is 2 cubed. So 2 to the 2x equals 2 cubed. Since the bases are the same, the exponents are also equal. So 2x equals 3. Let's solve for x. Divide both sides by 2. X equals 3/2. Okay, now let's check our work. Let's go back here. 4 to the 3/2 power, does that equal 8? Well, what's the square root of 4? That's 2. And 2 cubed is 8. Right? So we're relying on things we did back in chapter 9. You thought we were done with that. Ha! Oh no. We're still using that information. Okay. Now, this says evaluate each logarithmic expression. Log base 3 of 9. Okay. Well, this is a logarithmic expression, but I'm going to turn it into an equation, and I'm going to say log base 3 of 9 equals some unknown quantity that I'm just going to call box. Okay? Now I'm going to take this logarithmic equation and change it into an exponential equation. So 3 to the box power equals 9. But I could take 9 and write it as 3 squared, therefore the box equals 2. So log base 3 of 9 equals 2, because 3 squared equals 9. Any questions there? Okay. Log base 6 of 216. Evaluate the logarithmic expression. Well, I don't know what it is. I'm going to say that it's equal to some unknown box. But I could change this to an exponential equation now. 6 to the box power equals 216. Well, I wonder if 216 is a power of 6. Let's see. If I take 216 divided by 6, what do I get? Let's see here. 216 divided by 6. Oh, it's 36. So 216 is 6 times 36, but 36 is 6 times 6. So this would be 6 cubed, right? So the box equals 3. Log base 6 of 216 equals 3 because 6 cubed is 216. Okay. All right. Now we're going to use the calculator to find some values. This says use a calculator to find each value. Give answers to 4 decimal places. Okay. It says log 0.57. Notice there's no base written. This is log base 10. So I'm going to use the LOG button on my calculator, which is right about there. Okay. So push that button. Oops, it's a second. Oh, it's not. Here we go. Okay. So I've got log, I don't know what happened, something weird with my calculator. 0.57. Close it up, equals, I get negative 0.244125144. Round to 4 places, the 2 would round down. So negative 0.2441. Okay. Recall that when you're rounding to a certain place, you go 1 place to the right, 5 and above rounds up, 4 and below rounds down. Okay. Let's see here. Find the log of 375.876. So on my calculator, let's see what I get. Turn it on. Log of 375.876 equals 2.575044597. That's going to round here. The 4 rounds down, so I get 2.5750. Okay. Tell you what, let's look at the a calculator online here for just a minute. So give me a second here. And let's see, sign and click calculator. And okay. Now, this is not the same as the calculator that I've been using, but we've still got an LOG button here. Okay. So for instance, my problem was the log of 375.876. And there we have 2.5750, and the 4 would round down. Okay with that? All right. So let's go back to our whiteboard screen. And okay. Now, this says use a calculator to solve each equation. It says log of x equals 2.8945. The thing I've got to remember is that there's an implied 10 there, log base 10. So changing this logarithmic equation into an exponential equation, I get 10 raised to the 2.8945 power equals x. Now, on my calculator, there's two different ways I can do this. I can put in 10, use the little caret power key, and then 2.8945. Or, remember I said that the second function key of log was 10 to the x? I could go second, okay, and then I've got to turn the calculator on for a second. If I go second and then push the LOG button, which is actually the 10 to the x button, I get this. And then I put 2.8945 in there. So I can do that either way. 2.8945. And we get 784.33211. So this is going to round down. So we're going to get that to 4 decimal places. Okay with that? Right. Let's take a look at some logarithmic functions. This says stocking lakes, not as in stockings or as in stalking somebody, but stocking, we're going to put fish in a lake. It says a farmer stocked a lake on her property with 75 sunfish. She was told that with the proper oversight, the sunfish population could be approximated by the logarithmic function f of t equals 75 plus 45 times the log of t plus 1. Okay? Where t is the number of years since the lake was stocked. Find the number of sunfish you can expect in the lake in 2.5 years. So t is time in years. So 2.5 years, we're going to find f of 2.5. Okay, which would be 75 plus 45 times the log of what? 3.5. Okay, so on my calculator, 75 plus 45 times the log of 3.5. And I get 99.483. So rounding to the nearest fish, 99 sunfish. So about 99 sunfish. Any questions there? Okay, here's another application problem. It says children's height. The logarithmic function h of a equals 29 plus 48.8 times the log of the quantity a plus 1 gives the percent of the adult height of a male child a years old has attained. If a boy is 9 years old, what percent of his adult height will he have reached? So basically, h of 9 equals 29 plus 48.8 log of 9 plus 1, which is 29 plus 48.8 log of 10. Okay, now, again, we're talking log base 10. So 29 plus 48.8 times the log of 10, and I get 77.8, so 77.8% of his adult height. So that's saying that on average, a male child of age 9 has reached 77.8% of his adult height. That doesn't mean that's going to be true for every single individual, but on average. Okay. All righty, I think I've tortured you enough for today. Probably no one would argue with that. So for tonight, you've got section 11.3 and 11.4. I'll be back tomorrow at 10 a.m. with an office hour and at 11 a.m. with going on in chapter 11. So I'm going to stop the recording.